Hello and welcome to another podcast. This time we're starting out onto chapter 10. And so we're done with the alkane and alkyne reactions. We're actually going in what would seem like slightly flipped out order. We're going back to alkane reactivity. But the reality is the alkanes, because all the bonds are fairly stable, CH and CC bonds are strong, stable sigma bonds, they're not terribly reactive. And so one of the things we're going to learn along the way is that they pretty much only do one interesting thing. And I'm not sure interesting is a perfect adjective for it, but they form what's known as free radicals, and it requires a pretty good amount of energy to make these reactions happen. So for hydrocarbons, we use them for fuels because we know if we can burn them, turn the CH into CO, so turn all the CH bonds, all the fully reduced carbons into fully oxidized carbons, we can generate a lot of energy. But to do so, it has to go through free radical mechanisms, which means it has to occur at fairly strenuous conditions, high temperature, high pressure. So that's one thing about this particular section is a lot of the stuff we deal with is going to be under strained conditions. Okay, so I want to go back and revisit something we did early on in the semester, probably the very first week, where we talked about bond breaking. So bond association energy or bond breaking deals with a shared pair of electrons no longer sharing, so one or two ways can break. One of the atoms can get both electrons, leaving a negative charge on that atom and a positive on the other atom, which lost all the electrons of the bond. That's what's known as a heterolytic fashion, an unequal separation. One gets two, the other one gets none. In a homolytic fashion, it's what's known as a free radical reaction, or a split of the bond into one electron for each of the atoms. The problem with free radical splitting is that radicals mean will result in the atom having an odd number of electrons. It has all its electron pairs somewhere else, and then a single electron. And we know by octet stability that that is not a very favorable situation. So radicals become highly reactive. And briefly want to revisit something mentioned early on and going to go towards this at the end of the chapter. But O2 gas, for all this time in GChem, they showed me a double bond, but they should have in fact showed me what's known as a biradical. Because it's a biradical, it's highly reactive. And hence, we take advantage of that. We use it to oxidize hydrocarbons to generate energy. But the downside of that is that when you take oxygen into your body, it doesn't know what an energy molecule is versus any other molecule. So once it's inside your body, it can oxidize anything in its way. And so we hopefully can have it target energy molecules by putting it in its pathway. But occasionally we will start to oxidize. And we'll talk about something towards the end known as an antioxidant, which is a natural free radical scavenger, a molecule that will react with radicals generated by O2 and stabilize our body by picking those up so they don't run rampant and break us down. But all of our radical chemistry, the reasons we can burn things, reasons combustion exists, all those reasons stem from the fact that oxygen's actually known as a biradical. Okay, I'm going to erase that and get into the actual cleavage. So homolytic cleavage is what we're going to be interested in. And notice the arrows are single-headed. So we did that briefly when we did the HBr in the presence of peroxides forming an anti-Markovnikov addition reaction with an alkene. So we are somewhat familiar with the single-headed arrow, but we're showing it starting in the middle of this bond, and one of the electrons of the bond is going to L, one is going to Q. I chose L and Q because there's absolutely no elements with those letters, so there's nothing sacred or special about them, just to show that it can break in that way. Notice you have to put in energy, and light, generally speaking, is higher energy than heat when it comes to energetics. And so this could be light used in chemistry, at least. I probably should put it as like H nu, representing a photon. And that makes it a little more general. So let me actually do this. Let me get rid of light, get rid of my H nu, and put it right below there. And what it represents is any frequency that's strong enough to carry out bond breaking. And so we know we're not supposed to stare at the sun. We know the damage it can cause. It's because the UV rays it gives off can break sigma bonds and pi bonds. So it can just break our bonds. So consequently, light can be damaging. So light is high enough energy to break bonds, something you can hang on to in the collection of information you have. Okay, radicals are formed when it breaks in this way. Want to revisit heterolytic just for a brief moment? Heterolytic means ions are formed. This two-headed arrow represents two electrons moving over. So the Q is going to get both. The L gets none. So you end up with a plus on the L, negative on the Q. Okay, so fundamental difference. We are pretty much locked into radicals for the next span of time until we finish this chapter. So radical, again, highly unstable because it has that unpaired electron. It's constantly looking to try to find a pair. And in doing so, it can actually start reacting with things you don't want it to react with. So radical carbon can typically be treated as planar. In a frozen moment, if you had just a snapshot of it, it's highly unlikely that it's planar. It's this sort of resonating back and forth between two possible extremes. So one of those extremes could have the lobe up high and the radical in the upper lobe, hardly any electron density in the lower lobe, or electron density can be found mostly in the lower lobe, nothing in the upper lobe. And so notice that these three substituents, whatever they happen to be, are slightly down, slightly down, slightly down. Here's a slightly up, up, and up. So the bond angle might reduce all the way down to, I don't know, 116, 115. Here it might also be around 116, 115, but on average, as these things fold up and down, an angle is usually, or it can be averaged out to be 120. So it's going to be a trigonal planar scenario. We show an equilibrium because it's not actually resonance. We're not moving electrons from one point to another. So it's some sort of equilibrium between the two. And so we're going to consider radicals to be essentially planar. Whether you put the electron in the upper lobe or the lower lobe makes no difference. It's going to be the same story. So this is going to be how we visualize a radical. Going to visualize it as being planar, but we're going to note that it's constantly oscillating between the two states. Okay, so onward we march. Radical stability or lack thereof dictates how strong a bond is, the bond association energy. So if the radical is highly stable, it means it's not going to, it's not going to really be troublesome to form. So if it's a stable radical, it's going to go to very low energy, which means the bond association energy must be significant. If it's fairly unstable, then the bond barely takes anything to break because it's going to something less stable. So here, higher homolytic bond association energy determines a less stable free radical, means it goes up to less stable. So hopefully it makes sense. I think a picture will make more sense in this case. So if we consider the bond association energy along this path, this first carbon here is sp2 hybridized. So you'll form a vinyl free radical. So if it were to form a free radical, it would lose that H. And you'd end up with just a single electron here. And if you know from all our carbocation study, a carbocation on a sp3 is much better than on sp2. So that's why this one's so unstable. The next one, the methyl, no methyl donation, no alkyl donation to this carbon. So this again will be a situation where, although it's sp3, we're going to end up, when we get rid of that H, forming again a relatively unstable free radical. As we go all the way across, moving from left to right, you'll notice it goes from sp2 to sp3, sp3 with one R group donating in, sp2 or 3 with two R groups donating in, sp3 with 3 donating in, and then finally we get to something where it's got resonance stability. So if I lose this H, so I moved over to the 362 one, the vinylic, this free radical right here can resonance stabilize. So those electrons go there, those go there, those go to the end, meaning this free radical will be shared between this carbon and this N carbon. The sharing through resonance makes it more stable, which means it takes less energy to break that bond. So one thing I want to point out, I'm going to get rid of all the breaks I just showed and just make it all the way back to just the bonds. But keep in mind what we're talking about is the free radical cleavage of these 7 individual bonds. You'll notice these are essentially the same energy. And so just want to point something out. I don't know if many people are reading the book. I mean, it's a great reference, great for questions, but I don't know if, at least based on feedback, a lot of you take to reading books to learn your information. But for those of you who do, and you happen to be looking through the numbers, you'll notice the numbers I put here are different. And as I've said many, many times, the way these numbers are generated for probably a lot of authors, I can only speak on behalf of myself, but by looking at all the information out there and deciding which seems valid, which seems invalid, and averaging whatever all the valid numbers are, I come up with these. But they're different, and I just know the general trend. The trend is the same, although the numbers are different, except for right here. So whether it's vinylic, resonance stabilized by just a single double bond, or benzylic, where it's a radical to be stabilized by an entire benzene ring, there's pretty much just an argument as to which one is more stable. And so the numbers don't really bear it out. So I took average numbers from multiple sources, and it ends up the numbers are within their error bar of one another, which means we can't reach a definitive conclusion. So I'm going to say they are roughly equal. Allylic and benzylic are essentially equal when it comes to stability. I would never make you decide between that because it can't be decided. And that said, if you ever have to deal with this in another class, and they say, oh, allylic is more stable, then go with what they say. If they say benzylic's more stable, go with that teacher says. But the reality is they're essentially the same. Okay, so resonance stability, why does it help? So just again, reiterating, the lower bond association to the allylic and benzylic means it must be really stable, free radical we generate. So again, this one, this single electron, excuse me, can kick in. This pi bond can break, move one electron over here to form pi bond here, and move over. So it's not the typical resonance we're used to seeing with 2 electrons moving over, but it is still a case of electrons moving through a pi network. So this is what offers our stability in the vinylic. And for benzylic, notice that this electron's at the N carbon where we, let's say, broke a CH bond and had a free radical. What it can do is it can move in, and this pi bond here can break, and leaving with a free radical right here. But that can now move over. So this can move to there, that pi bond can move there, that electron can go to that spot. So now you have it on this location. So it went from the end over here to what's going to be known as the ortho position, now the para position. So it went from ortho to para, and then it can go in one more time. This can kick in, breaking that bond, moving that one to there. Now you end up at the other ortho position up here. So again, just to mention what I was saying, if this is my substituted carbon, one away is known as ortho. So these are both ortho positions. And then the one at the very, very end is known as para. And that'll become a little more important as we get into benzene chemistry. But what you'll learn is that whenever you do resonance, it is the ortho and para positions that can take on charge, or in this case, a free radical. Okay, so here's where the controversy stems from. So as mentioned, there's a dispute in the literature as to which is more stable. I mean, both are compelling arguments, but the reason some people say one or the other, this only has like one spot the electron can, or the single electron can move from here. It can move to this spot. So there's 2 resonance structures. Here, it has 1, 2, 3, 4 spots it can go, so 3 spots it can move to. So because it can be shared over a greater area, the people who say this is more stable say it's because it has more resonance structures. But the flip side of the argument is all these resonance structures break aromaticity as we typically know it, because now the electron density has gone here. Because of that situation, it isn't all contained within the network, so they say it loses what we're going to call aromatic stability of having all the electrons, 6 electrons, in the cyclic system. So again, who knows who's right? There's an argument for both. I'm going to say again, they're about the same number. Okay. So stability. Resonance stability is key, and hang on to that. Tertiary is better than secondary. Secondary is better than primary perspective based on the R groups donating in. It's also very important. And so what we're going to do with it in the next podcast is we're going to start looking at how reactions occur. So if you can have a tertiary, secondary, or primary free radical, reaction would prefer to have tertiary wherever it can. And so there's going to be a favoritism of reactivity for tertiary over secondary over primary. But for now, we are done with the introduction, and next podcast we'll get into more of the reactivity. Thanks for tuning in, and I hope you have a wonderful day, and stopping it now. Bye.